Today we're going to be talking about probability distributions of random variables. In this example, x is the number of cats owned by a randomly chosen individual. Okay, so we can collect some data. We have that data. It starts with 0, 1, 1 and keeps going. I'm not going to list all the data. It's there listed, so I'm not going to say it. Because I have data and we have the formula for observational probability, I can form the probability x equals 0. That's the observed number of counts of 0 cats divided by the total number of outcomes. We can see that we randomly selected 10 individuals. The first individual owned no cats. The second individual owned 1 cat. The third individual owned 1 cat. The fourth owned 0. And the fifth owned 3, etc. Okay, so using that data, we would count the number of individuals that own 0, there's 3 of them, out of the total, 10. So we get the observed probability of 3/10 for the probability x equals 0. Okay, if we wanted to calculate the probability x equals 2, we just count how many people own 2 cats, and that would be 2 out of 10 individuals. And we have the probability listed in the second column here, and we see that when we add them up for the total, we get 10 out of 10. That's a good thing because that's one of the axioms of probability. Total probability equals 1. Okay. So just as an example, we can calculate the probability someone owns more than 1 cat. And this asks us to calculate probability x is bigger than 1. Another way of writing this would be x bigger than or equal to 2 because they're integer outcomes. And the only outcomes that are bigger than 2 are x equals 2 itself and x equals 3. When we add those, we get 2/10 plus 1/10, so 3/10 or 30%. Okay. Now, with this data, one thing that we could ask is, what's the average number of cats an individual owns? That is, on average, how many cats would a randomly selected individual own? Okay. So this is synonymous for expected value, and let me go over this. So well, the average here, one way of denoting an average is with a bar, x bar. That's going to be common notation. And with data, hey, we have data right here. With this data, I can just add it up and divide by the total number, right? So here's that data. And it looks like I made no errors in writing it down. So instead of these commas, I'm just going to put addition symbols. So that's adding up all the data Then I need to divide by the total number. Well, that's 10. Let me rewrite this. One way of writing this is, hey, I can group all the zeros. There's 3 of them. So that will be 0 times by 3/10, because there's 3 zeros. Then I have the ones. How many ones do I have? I think there's 4 ones. So that will be 1 times 4/10. Now I'm going to count the number of 2's. There are 2 2's. So that's 2 out of 10, because everything is divided by 10 after all. And finally, I'm going to count the number of 3's. There's 1 3. So it's just going to be 1. 3 times 1. Everything's divided by 10. What you should notice is, hey, these numbers, 3/10, 4/10, 2/10, 1/10, they look very familiar. Those are the probabilities. So we took the value of x and multiplied it by the probability. So this will be the summation of x times by p of x. And one way of writing sum everything up would be from minus infinity to infinity. It just turns out that probabilities for negative numbers are 0, and probability of a number being greater than 3, or excuse me, x being greater than 3, would be 0 probability. Okay. One thing that would be good to do here is to compute, is to give you the mathematical notation associated with this average. So for us is going to be e of x, and our convention is to call this the expected value of x. Okay. So in general, this is the expected value of x formula. And you might wonder, hey, what is this value? Because after all, it represents the average number of cats. Is going to be 1.1. And please don't round to 1. The 0.1 has significance. Okay. Now, just a few notes about expected values. Expected values properties is, hey, the expected value of a function of a random variable is going to be the sum, and we could do minus infinity to positive infinity. Another common notation is for all outcomes in the sample space, because the sample space is where we have non-zero probability of h of x times by p of x. Okay. We also have, so that's one property. A second property is that a constant times a random variable is just that constant times the expected value of x. And finally, the expected value of 2 random variables that are added is just the sum of the expected values. Okay. Now, there's one more example that I want to go over, which is variance. Now, variance that is an expected value, and it's the expected value of x minus the mean squared. This is the variance of x, and I should add one more common notation is to denote the expected value here by mu. So I wrote mu is x times p of x. All of these equalities are equal. So here the mean is the expected value. Okay. If you use the properties above for expected value, you can show that variance is the expected of x squared plus the expected of x quantity squared. Excuse me, not a plus there, but the minus. A little typo. And of course, we can also write this as e of x squared minus mu squared, because I told you mu is the symbol for e of x. Okay. Now let's calculate it. In the example, so we already calculated the mean number of cats was 1.1 squared. So we already calculated that number. The only thing that's left to calculate is this e of x squared. And that's going to be the summation from x being 1 to 3 of x squared times p of x. Now we just need to remember what p of x is in each instance. Okay, so x squared, it starts with 0 squared. It multiplies by probability of x being 0, so that's going to be 3/10. The next one is 1 squared, and it multiplies by the probability of 1, which is 4/10. Next, we're going to take 2 and square it, multiply it by the probability of 2. The probability of 2 is 2/10. And finally, we're going to take 3, square it, multiply it by the probability of 3, which is 1/10. Okay. So we need to sum these values. That gives us 2.1. So the variance is 2.1 minus 1.1 squared. We need to figure out what is the variance then. So in this instance, 2.1 minus 1.1 squared gives us 0.89. Okay. Now, one thing that we should notice is that in the calculation of e of x squared, that was 0 squared, that represents 0 squared cats, 1 squared, 1 squared cats, 2 squared, which is 2 squared cats. So what I'm getting at here is that the unit is cats squared. That isn't that pleasing because I haven't seen too many square cats. I've seen one or two, very fast cats that are basically square. But I haven't seen too many of them. So it's common to take the standard deviation so that we have our original unit. Okay, and that's called standard deviation. Standard deviation is the square root of variance. which is the square root of the expected of x minus mu squared, and that is the square root of the expected of x squared minus mu squared, which is the square root of 0.89, and that gives us units of cats. Now, this will give us a standard error or standard deviation of 0.79 cats. So that's the standard error. I'd like to point out, if we think about the variance, it's saying what's the expected of x minus the average squared. So on average, how far does an observation lie from the average squared distance? That's what variance says. Now I'm going to just give you a few properties of variance, just like I gave you properties of expected values. So your first property is that the variance of a constant is 0. It has no variation at all. Your second rule is that a variance of a constant times by a random variable is that constant squared times by the variance of that random variable. Okay. And your last one says if, that's a big if, x and y are independent, then the variance of x plus y is just the sum of the variation. Okay, thank you very much.